Welcome back to AI Academy. Today, we're diving deep into one of the most powerful machine learning frameworks in the world, TensorFlow. Whether you're a complete beginner or looking to level up your ML skills, this comprehensive guide will take you from zero to building your first neural network. If you find this helpful, don't forget to hit that subscribe button and the bell icon for more AI and machine learning content. Here's what we'll cover in the next 20 minutes. We'll start with the fundamentals, what TensorFlow actually is, explore why it's become the go-to choice for ML engineers, walk through installation and setup, build our first model together, and see some mind-blowing real-world applications. So grab your coffee, let's get started. So what exactly is TensorFlow? Think of it as your Swiss Army knife for machine learning. TensorFlow is Google's open-source machine learning framework that lets you build, train, and deploy ML models at scale. But here's the cool part. It's not just for experts anymore. Let me give you some quick history. Google released TensorFlow in 2015, and since then, it's been downloaded over 180 million times. Companies like Uber, Airbnb, and even NASA use it daily. What makes TensorFlow special? Three key things. 1. Flexibility. You can run it on your laptop, in the cloud, or even on your phone. 2. Ecosystem. It has tools for everything from research to production. 3. Community. Millions of developers contributing and sharing knowledge. At its core, TensorFlow works with something called tensors. Think of them as multi-dimensional arrays that flow through computational graphs. That's literally where the name comes from, TensorFlow. Now, you might be thinking, why TensorFlow when there are other frameworks like PyTorch or scikit-learn? Here's the truth. Each has its strengths, but TensorFlow shines in several areas. 1. Production ready. TensorFlow serving makes deployment super easy. 2. Mobile support. Run models on Android and iOS with TensorFlow Lite. 3. JavaScript support. Yes, you can run ML in the browser with TensorFlow.js. And 4. Visualization. TensorBoard gives you incredible insights into your models. The numbers don't lie. TensorFlow has 35% market share in machine learning frameworks, and it's the most starred ML repository on GitHub. Before we dive into code, let's talk about what you need to know. Don't worry, the bar isn't as high as you think. Required: basic Python knowledge. If you know variables, functions, and loops, you're good. High school math, understanding of basic algebra and statistics. Helpful but not required: some NumPy experience. Basic understanding of neural networks. If you're missing some pieces, don't worry, I'll explain everything as we go. And I'll leave helpful resources in the description. Let's get TensorFlow installed. I'll show you 3 ways, from easiest to most flexible. Method 1. Google Colab, recommended for beginners. The easiest way? Google Colab. It's free, runs in your browser, and TensorFlow is pre-installed. Just go to colab.research.google.com and start coding. Method 2. Local installation with pip. For local installation, it's surprisingly simple. Method 3. Anaconda. If you're using Anaconda, let's verify everything works with a quick test. Now for the fun part, understanding how TensorFlow thinks. There are 4 core concepts you absolutely need to know. Concept 1. Tensors. First up, tensors. Think of them as containers for data. 0D tensor equals scalar, just a number. 1D tensor equals vector, like a list of numbers. 2D tensor equals matrix, like a spreadsheet. 3D plus tensor is multi-dimensional arrays, like a cube of data. Let me show you each type with actual code. First, tf.constant creates immutable tensors. They can't be changed once created. Scalar equals tf.constant of 42. This creates a 0-dimensional tensor. It's just a single number, like temperature, 42 degrees. Vector equals tf.constant of 1, 2, 3, 4. This is one-dimensional, like a list of numbers. Imagine daily temperatures for a week. Matrix equals tf.constant of 1, 2, 3, 4. This is two-dimensional with rows and columns. Think of it like a spreadsheet with 2 rows and 2 columns. The 3D tensor is where it gets interesting. 1, 2, 3, 4, 5, 6, 7, 8. This could represent multiple matrices stacked together, like multiple spreadsheets in a workbook. When you print these, TensorFlow shows you the shape, data type, and values. The shape tells you the dimensions, super helpful for debugging. Operations are what we do with tensors. Add them, multiply them, transform them. Now let's see operations in action. This is where TensorFlow really shines. For addition, we create two vectors, A equals 1, 2, 3, and B equals 4, 5, 6. When we do tf.add of A and B, TensorFlow adds them element-wise, first element plus first element, and so on. So we get 5, 7, 9. The cool thing is, you can also just write A plus B. TensorFlow automatically converts it to the tensor operation. Matrix multiplication is more complex, but super important. We have two 2x2 matrices. tf.matmul performs proper matrix multiplication, not element-wise. It follows the mathematical rules: multiply rows by columns. For example, the top left result is 1 times 2 plus 2 times 1 is 4. The top right is 1 times 0 plus 2 times 2 is 4, and so on. This might seem basic now, but these operations are the building blocks of neural networks. When your model learns, it's doing these millions of operations. Concept 3. Graphs and sessions, TF1.x versus TF2.x. Here's something important. TensorFlow 2.x is much simpler than the old version. In TF1.x, you had to build graphs and run sessions. It was complicated. Look at this code. X equals tf.constant of 3.0. Y equals tf.constant of 4.0. Z equals x plus y. When you run this, you immediately get the result. This is called eager execution. Operations execute immediately, just like normal Python. But here's the smart part. If you need the performance benefits of graphs, which can be much faster, you can still use them. The @tf.function decorator converts a regular Python function into a TensorFlow graph. When you call compute z of 3.0, 4.0, TensorFlow compiles it into an optimized graph behind the scenes. First call might be slightly slower as it compiles, but subsequent calls are lightning fast. This gives you the best of both worlds: easy development with eager execution and production performance with graphs. Concept 4. Variables versus constants. This is a crucial concept that trips up many beginners. Let me explain the difference. tf.constant of 1, 2, 3 creates a constant tensor. Once created, you cannot change its values. It's immutable, like a stone tablet. tf.variable of 1, 2, 3 creates a variable tensor. These can be modified using methods like assign. See how we changed it from 1, 2, 3 to 4, 5, 6? Why does this matter? In machine learning, your model needs to learn. The weights and biases in your neural network start with random values and gradually improve through training. Constants are perfect for your input data. That doesn't change. But variables are essential for model parameters that need to update during training. Think of it this way. Constants are your training data, fixed. But variables are your model's brain, constantly learning and updating. Time to build our first model. We'll solve a classic problem, predicting house prices based on size. Don't worry, I'll walk you through every single line. Step 1. Create sample data. Let me break this down line by line. First, we're importing our essential libraries: TensorFlow for machine learning, NumPy for numerical operations, and Matplotlib for plotting. Next, I'm creating some realistic sample data. We have house sizes ranging from 1,000 to 2,400 square feet, and their corresponding prices from $150K to $360K. Notice the clear relationship. Bigger houses cost more. Now, here's something crucial: normalization. we're converting our data to have a mean of 0 and standard deviation of 1. Why? Because machine learning algorithms work much better when all features are on the same scale. Without this, our model might struggle to learn properly. Step 2. Define the model. We'll use Keras, which is now part of TensorFlow and makes building models super intuitive. Okay, this is where the magic happens. Let me explain each part. First, tf.keras.sequential. This creates a sequential model where layers are stacked one after another, like building blocks, perfect for simple models. Inside, we have tf.keras.layers.dense1, input shape equals 1. This is a fully connected layer. The 1 means it has one output neuron, and input shape equals 1 means it expects one input feature. So we're saying take one number in, give one number out. Now for model.compile. This is like preparing your model for training. We're choosing optimizer equals Atom. Atom is like a smart algorithm that adjusts how fast our model learns. Think of it as cruise control for learning. Loss equals mean squared error. This tells our model how to measure mistakes. MSE is perfect for predicting continuous numbers like prices. Metrics equals MAE. Mean absolute error helps us track how well we're doing in units we understand, dollars. The model.summary shows us exactly what we built, like a blueprint of our neural network. Step 3, train the model. Now comes the magic, training. The model will learn the relationship between house size and price. This is the most exciting part, watching our model learn. Let me explain what's happening. Model.fit. This is where the actual learning happens. We're passing our normalized house sizes and prices, saying, learn the pattern between these. Epochs equals 100. An epoch is one complete pass through all our data. So our model will see every house size price pair 100 times, getting smarter each time. Verbals equals 0. This just keeps the output clean. If you want to watch the training happen live, set this to 1. The history object is like a diary of our training process. It remembers how well the model performed at each step. Then we plot two crucial graphs. Loss over time. We want this going down. It shows our model making fewer mistakes. And the MAE over time, this shows our average error in dollars, also should decrease. If you see these lines going down and flattening out, congratulations, your model is learning. Step 4, make predictions. Now for the moment of truth. Let's see how well our model learned. First, we create some test house sizes that our model has never seen before, 1,100, 1,500, 1,900, and 2,300 square feet. Remember normalization? We need to apply the same transformation to our test data using the same mean and standard deviation from our training data. This is super important. Always use the training statistics. Model.predict. This is where we ask our trained model, based on what you learned, what do you think these houses should cost? But wait, our predictions are still normalized, so we need to convert them back to real dollars using the reverse transformation. That's what this line does. Predictions.norm times houseprices.std plus houseprices.mean. The for loop prints out our results in a readable format. You should see something like 1,500 square foot house, 210K. Pretty cool, right? Finally, we visualize everything. Blue dots are our training data, red dots are our predictions. If our model learned well, the red dots should follow the same pattern as the blue dots. This scatter plot is your model's report card. If the predictions look reasonable compared to the training data, you've successfully built your first machine learning model. This was a simple linear model, but TensorFlow can handle much more complex architectures. Let me quickly show you what a more sophisticated model looks like. Don't worry, you don't need to understand every detail yet, but it's good to see what's possible. This model has multiple layers. First layer, 64 neurons with ReLU activation. ReLU just means if the number is negative, make it 0. It helps the model learn complex patterns. Dropout 0.2. This randomly ignores 20% of neurons during training. It's like forcing your model to not rely too heavily on any single neuron, prevents overfitting. Second layer, 32 neurons, also with ReLU. Output layer, 1 neuron for our final prediction. This creates a neural network that can learn much more complex relationships, like if house price depends on size, but also location, age, and number of rooms. Now let's see TensorFlow's real power. Let me show you how easy it is to work with text and images. Natural language processing example. Let's build a sentiment analyzer that can tell if movie reviews are positive or negative. Let me walk you through this sentiment analysis model step by step. It's actually simpler than it looks. First, our sample data. We have movie reviews and their sentiment labels. 1 means positive, 0 means negative. Simple. Now, here's the challenge. Computers don't understand words, only numbers. So we need to convert text to numbers. Tokenizer does this magic. Num words equals 1,000 means we'll only keep track of the 1,000 most common words. OOV token equals underscore OOV, stands for out of vocabulary. Any word we haven't seen gets this special token. Fit on texts.reviews, this tokenizer reads all our reviews and creates a vocabulary dictionary. Word amazing might become number 15, terrible might become 8, etc. Text to sequences converts our text reviews into lists of numbers. This movie was amazing might become 4, 12, 7, 15. Pad sequences makes all sequences the same length by adding zeros. Why? Neural networks need consistent input sizes. Now for the model architecture. Embedding of 1016, input length equals 10, converts word numbers into dense vectors. Think of it as giving each word a personality with 16 traits. Global average pooling 1D averages all word embeddings into one vector representing the whole sentence. Dense 24, activation equals ReLU, a hidden layer for learning complex patterns. Dense 1, activation equals sigmoid, output layer, sigmoid gives us a probability between 0 and 1, perfect for positive-negative classification. This model can now read any movie review and tell you if it's positive or negative. Computer vision example. And here's how easy it is to classify images using a pre-trained model. This is one of my favorite features of TensorFlow, using pre-trained models. Let me break this down. tf.keras.applications.mobilenet2, this loads a pre-trained model that Google already trained on millions of images. Weights equals ImageNet means it learned from the ImageNet dataset with 100 different object categories. The best part? You don't need to train anything. It's ready to use right away. Now, let's understand the classify image function. Load image, image path, target size equals 224 by 224, loads your image and resizes it to 224 by 224 pixels. Why this size? That's what MobileNet 2 was trained on. Image to array converts the image to a numeric array of numbers that the model can understand. tf.expand dims image array 0 adds a batch dimension. The model expects multiple images, so even for one image, we need to make it look like a batch of size 1. Pre-process input. This applies the same pre-processing that was used during training. Super important for good results. Model.predict, this is where the magic happens. The model analyzes your image and outputs probabilities for 1,000 different object classes. Decode predictions converts those probability numbers back into human-readable labels with confidence scores. So you could upload a photo of your dog and it might return 1. Golden Retriever, 0.87, 2. Labrador, 0.09, 3. Dog, 0.03. Amazing! You can also build custom convolutional neural networks. Let me blow your mind with what's being built with TensorFlow right now. Healthcare applications. Google's DeepMind used TensorFlow to create AI that can diagnose eye diseases better than human doctors. We're talking about saving millions from blindness. Self-driving cars. Tesla, Waymo, and other companies use TensorFlow for computer vision in self-driving cars. Every time a Tesla recognizes a stop sign, that's TensorFlow at work. Language translation. Google Translate serves over 500 million people daily, translating 143 languages, all powered by TensorFlow. Here's a quick demo for language detection. Creative applications. Artists are using TensorFlow to create music, generate art, and even write poetry. The possibilities are endless. Business applications. Netflix uses TensorFlow for movie recommendations, Spotify for music suggestions, Uber for demand forecasting and route optimization, Airbnb for price optimization and fraud detection. Wow, look how far we've come in just 20 minutes. We explored what TensorFlow is and why it's dominating the ML world, got it installed and running on our machines, built our first model from scratch, saw real-world applications that are changing the world. So what's next on your TensorFlow journey? Here's my recommended path. Beginner level. 1. Practice with more Keras models. 2. Try the TensorFlow tutorials on tensorflow.org. 3. Work with different datasets from Kaggle. Intermediate level. 1. Learn about different model architectures. 2. Explore TensorBoard for model visualization. 3. Try transfer learning with pre-trained models. Advanced level. 1. Custom training loops with gradient tape. 2. Model deployment with TensorFlow serving. 3. Mobile deployment with TensorFlow Lite. I've put together a ton of resources for you. All the code from today is in the description, links to the best TensorFlow tutorials, dataset recommendations for practice, my favorite TensorFlow YouTube channels. If this video helped you understand TensorFlow, please give it a thumbs up. And if you want to see more AI and machine learning content, hit that subscribe button and ring the notification bell. What would you like to see next? Comment below with your requests. Next week, I'm diving deep into building a complete image classifier that can recognize different dog breeds with 95% accuracy. You won't want to miss it. Thanks for watching, and I'll see you in the next one.